And with regard to detection of gravity waves, there is a tension that the web of the field is of Planckian scale, and there is an interesting idea of assisted inflation, where there are many fields, and this slightly relaxes this bound. The individual field web is not just n Planck, but it may be divided by a square root of n, and if n is 10 to the power 2n, then we can have few orders here.
That's why I myself don't believe on it. It's very hard.
Yes, I'm going to tell about this exactly the same. Yeah. As I told you, first in string theory, the proper model was not derived, so it will be very hard, but let me come to this. Yeah, I agree. So field theory models so far. How about relation to supersymmetry, supergravity, and string theory? So if any of these models are related to string theory and supergravity, it becomes a particularly important issue of the fundamental physics, and we need new data from Planck class polarization as long as C and D fall. And the reason is the, for example, the picture which Andrei Linda showed you yesterday. So it is after pi squared, there is a lot of room here, and you can still have this R much below 0.1 for a very simple model like that. Moreover, if you have 5 squared and 5 cubed and 5 to the 4, you cover completely the total area in RNS plane. Now, this is from David Lies, and what is important, what I would like to stress here, is that we have some detectable level of gravity wave from chaotic inflation, from natural inflation. It goes a rather long way here. So even after Planck will not discover gravity waves, we still have to wait for another order of magnitude because these models are going now below 0.1. Now, the goal of technology community for a long time was to reconstruct from the data some information on the inflationary potential. And this is still a valuable goal. However, in the context of string theory and effective supergravity, the goal is to get some information on Taylor potential and superpotential. And generic potential of n equals 1 supergravity depends on some number of complex scalar fields which have a geometric meaning of coordinates in Taylor geometry. And this is a reminder that when we know the potential, we have the ingredients are superpotential and Taylor potential. So then the question is how you get models of inflation which predict gravity waves, but not at the level of field theory, but at the level of supergravity. Then you may hope to get them from string theory. So the problem with chaotic inflation in supergravity was known to persist for canonical Taylor potential, and the problem was of the following nature, that this exponent at large phi blows up, and therefore it completely kills inflation. And it was solved only in 2000 by this group of people, and what they did, they took a shift symmetric Taylor potential. So phi plus phi bar is here, but the phi minus phi bar, which is the axiom, is not. And then they added a small superpotential which breaks shift symmetry a little bit. As a result, one finds that this effective field theory model, which does predict gravity waves, could come from this kind of supergravity model. This model was not derived from string theory yet.
Just to comment, this is not protected in principle because phi and x are all actually base fingers. One can write down.
Yes. Yes. So the statement is there is an effective supergravity model, and so if shift symmetry is broken only by this term, then you can explain gravity waves because in the end of the day we may see them. So we are looking for any explanation.
So what would prevent other breaking of that symmetry in other terms you generated?
Okay. With regard to supergravity, it is difficult to say what kind of corrections you should expect. It's not renormalizable anyway. So if this effective supergravity allows you to compare what you see with what you write, then at least we are trying to find it. Now, with natural inflation, nothing was known, and just recently I came up with an extremely simple model. So you just take shift symmetric quadratic Taylor potential with one complex field. You take, everybody has seen this type of superpotential constant and the non-perturbative piece. You do the uplifting, and then you find the potential such that it has a minimum for the radial variable, and the radial direction is extremely steep. Therefore, the radial direction wants to go to the minimum, and at the minimum of the potential, we nicely recover this natural inflation, which has this famous tail, so it has grown to very small r, which could be detectable even in the second range of detectors. So here is what I call this axion value potential. So as you see, there is a very sharp minimum in radial direction and extremely shallow valley here for the axion going from 0 to 20. But if I look at the same potential between 0 and 300, you see the periodic nature of this potential. And so the natural inflation potential is the slice at the bottom of the valley. And it is coming from extremely simple supergravity. As well as chaotic inflation in supergravity was not derived from string theory the same theory. But at least we have a gravitational version of the model, which if the parameters are proper, and if the p-mode will be discovered, we have supergravity version of it. Now, there are models of inflation, therefore, in supergravity which predict tensor modes below the current bound all the way up to 10 to the minus 3. And in all known cases, they have shift symmetric quadratic Taylor potentials. And we'll have to wait till 2018 plus before we know if such models are valid. And of course, by that time, we will hopefully know about supersymmetry, whether we should deal with Taylor potential and superpotential at all, if supersymmetry is there. And so in string theory, the computable Taylor potentials in known cases of Calabi-Yau complexification have shift symmetry. However, they are logarithmic. They are not quadratic. They look approximately like that, where T-I-G-K some Calabi-Yau intersection numbers. For example, the simplest models of TPLK has this tensor just T111 equals 1. And these models generically predict undetectably small tensor modes in inflation. This is an example of such method. Now, the reason why this happens and why inflation has not been implemented so far in string theory is, again, we just look at TPLC model and we take this Taylor potential, we take this super potential, and it turns out, if you look at the plot, you see the following, that axion is as steep as the radial modulus. And this is an abstraction to inflate inflation models assisted inflation in known models of string theory. And therefore, there are no detectable gravity waves in these models, which are generic, which have stringy logarithmic Taylor potentials. Yes, please. Do you count my time?
But it's not correct. There are many mistakes in the figure.
I will. Let me just try to bring you, because I started kind of new agenda. It was George Stas a few years ago who is working on all these beam modes, and he asked it what it has to do with fundamental physics. And at that time we were not aware, and we just started. So what I'm trying to say here, that the axion is as steep as a dilaton. And if you have supersymmetry, you always have complex fields. So you just don't have simple axion physics which could coherently assist. Here is another model which I have a suspicion that it may work well. And this is not a regular Calabi-Yau, this is a K3 Calabi-Yau times an Orienti fold. And this is the well-known picture of this space. And it has a particular Hodge-Keller manifold associated with some symmetry. And so if the modulus is fixed, and if x0 is fixed, which has some particular meaning, there are 19 other modulus here. And if those two are fixed, in principle, this law can be extended. And then we are getting something like quadratic shift symmetric potentials. And those are very natural here because we do have component instanton. And so if we can make this model working at small values of this model which are subtracted from here, that would be quite interesting. They may reproduce this actual value potentials of the gravity, predicting gravity waves. But this is work in progress. I don't know the answer because we need very specific numbers in natural inflation models to predict gravity waves. For example, we need a large period. So numerically, I don't know. However, qualitatively, we can have shift symmetric quadratic Taylor potentials. And if I have 1 minute, I'd like to show the movie which shows you what kind of modular we're talking about. This is a movie done by Paul Aspinwall. So you see, it is this volume modular which blows up the singularity, and the corresponding, so when it settles to a particular minimum, then the axion partners of this module volume, of these cycles may help to work for the axion type model. Okay, so I'm about to conclude. In the context of inflation in string theory and gravity, the detection, as well as non-detection of the tensor modes from inflation, is of crucial importance. And unfortunately, it will take a very long time. At the present level of understanding, there seems to be a unique way to read the features of the Taylor potential from this graph. This, however, may change because we just started and some people may just find out other things, but this is at the present level. So if there is no detection, we can say Calabi-Yau threefolds, which are generic logarithmic Taylor potentials, it was their prediction that R had to be much less than 10 to the minus 3. So we can say this is then, we are just fine. We have this class of models which we studied most of the time, and they just predicted. And therefore, all people, this enormous effort to detect B modes, which I know from people who are putting their life in the next 15 years on this, is not wasted because it tells us that this famous, well-known corner of the landscape is the one which we can work and study. If, however, there is a detection, it will tell me, from all I know today, that shift symmetric quadratic Taylor potentials easily give R in this range, from the current bound all the way up to the level of detection. And there is an issue whether we can actually derive them from string theory or not, but at least they are available now in supergravity. Now, there is this other point about the mass of gravitima, and the fact that in known models it is tied to future detection or non-detection of tensor modes in the most developed string theory models. So let me remind you that the scale of gravitina, they could be either light or supersymmetric particle and represent dark matter, or they could be at 1 TeV, or they could be extremely heavy. And we simply don't know. And there is nothing today which would tell us which of these is, will be happening. Now, if we learn that they are extremely light, all the way up to 1 TeV, this would mean that either we have to use in string theory this model with fine-tuning, which avoids the bound, or we simply need new ideas here. If, however, they will be found to be indeed super heavy, then all models of inflation like racetrack, large volume compactification, and other models, they will easily survive this kind of
Actually, I would like to return your question. You were asking us Sunday whether we could measure W different from compound. And now today you were saying that the only thing you've seen so far with mechanical string theory would be that like a quantum compound. But then my question to you is, if we will go and measure something that looks like quintessence, to what extent can you actually even falsify all of string theory back to that?
No, so exactly this is what I was trying to have not too many slides, but this axiom value model which I showed you has an extremely nice, extremely shallow axiom direction, and I believe under pressure of data, this model will be one of the choices, one of my choices, because there is no contradiction to free flow. And so now we have a model which is consistent with supersymmetry, which means supergravity will make the cosmology. So I was planning to say that as a candidate of dark energy, not cosmological constant, this is a model which I will start using. And this is why I asked, do I have to do it now or I can postpone it?
I have one question and one comment. The question is that is there anything which can really distinguish string motivated models from this, usual physics models? Which can distinguish, which can tell me that okay, we have the data and the size is coming from the string motivated side, or it's coming from the.
Okay, I was thinking about it, and so there are a few levels of answer. So if supersymmetry is there, I would say with regard to cosmology, we have to deal at least with supergravity. And then the question is, not every supergravity we know how to derive from string theory. Some we know, some we don't. This is the easiest example. Quadratic shift symmetric Taylor potentials are not that often, whereas logarithmic are. And so if supersymmetry will be our way of developing, then this will be where the difference will come between those models of supergravity which are derivable in the context of 10 or 11 dimensions with whatever string theory believe is valid, or it is some 4-dimensional supergravity which represents the data. And I think people may think about it.
And the comment is that, well, it's fair to say that string theory can provide many models of inflation. And as I also mentioned to Andre, that now perhaps it's important to think about that, whether, in order to really connect with phenomenology, it's really important that somehow the inflation and the Stein model or MSSM, whatever we call it, should be connected. And somehow
I agree with you. For example, this talk we had by Enquist on standard model inflation, this is extremely low H. And it may be upon us because the combination of these models may be required.
All that I'm saying, the effort should be kind of divergent into this direction also on the string.
Yeah. So sorry, I didn't answer this. Can you repeat the question? You want to fix the module so that by the exit of inflation, all moduli are fixed. And the model which you mentioned by Krause and Beckers, they do have an assistant effects via like something like 70 M5 rings. But I believe their model does not predict gravity waves. Anyway.
Besides that, they have a
there are issues there, but I believe they don't predict gravity waves. So what I'm trying to say that as shocking as it was with experimental discovery of dark energy / technological constant, the future discovery of gravity waves will be also a shock unless we are prepared from the fundamental physics.
Amanda?
I wouldn't formulate it like that. It's just the models which we know always, they just don't predict gravity waves. We just went case by case, and as I told you, my larger paper on this with my collaborators should be out soon. We just explore everything which we know and trust. And we see no way to predict gravity waves unless we simply switch to this quadratic shift symmetric Keller potentials, which are somewhat unusual, they easily give you gravity waves. Which doesn't mean that there are no other things. We just consider this as an invitation to look into this.
I think Fernando is right. They have to be small fields because the surface to scalar ratio is equivalent to the slope of the potential.
That is true.
And that can only be absolutely small.
I agree.
Anyway, I'll just
I agree. I would say that indeed they are all small fields, but it is not because it was our intention. But that's the way it is. So you can turn it in the following direction. If they don't find gravity waves, this is what standard corner of a landscape, which we know how to study, was predicting. On the other hand, what is important that there are many non-computable Keller potential in the theory. And Calabi-Yau is a case where we know it, but in many other cases we simply don't know it. We almost will be reading them from the start if they detect the waves. Oh, yeah, as I told you, to get in nature inflation gravity waves, you have a very specific situation with so-called axion coupling constant. And there are lots of interesting things there on which we are working in our paper now. So we're checking things. And indeed, numerically, it is very tough to get the large period. On the other hand, when you have supergravity, you just write whatever you want and you easily get it. The question is whether you can get it from any fundamental construction.
The same to emphasize that the other parameters has to be smaller than the rest of the mass. It's more general than the example that you gave. The mass drawn by various people in the early 90s from banks and collaborators who did their work on this conversion. It's true in supergravity. It's not specific to the KKT construction.
The Hubble versus Gravitino?
The Hubble parameter has to be smaller than the gravitational mass, which is quite a correct.
Thank you, I didn't know this. Perhaps you will give me the reference. Here it is just obvious. You're saying it is more general.
Much more general.
Which makes the situation even more tense, because if Gravitino is light, then we have problems. We have to go to extremely low scale of
There is
inflation.
nothing wrong with that. You can do inflation down to the electric scale and even below that. If you are prepared to inflate a small speed values, because you can get the right amplitude of density correlations by balancing a small numerator by a small denominator.
However, if it is light, a supersymmetric particle sitting in dark matter, I have heard on TV, and extremely light, then you may not like it. And you may try to look at the models which avoid the bound.
So this is what exactly happens in this Asian inflation, that you can avoid this boundary.
Okay, so we'll have to study this.
Third comment on the past. Well, banks have told many different things in the past. And some of them are right, some of them are wrong, and some of them are based on guesses. The fact that at that time and until 2003, there was zero inflationary models based on string theory. So whatever bound to conjecture, well, I don't know what are models.
My remark was that is a statement about the tension between supersymmetry and the vacuum energy needed to drive inflation, which is true for any model with a supersymmetry. It's not specific to the string.
So in supergravity, you can easily violate it. In supergravity, you can easily violate it, and it's known. So
you can have a Hubble parameter bigger than the gravitational mass.
Of course.
I'm not aware
That was the example of the model Renata mentioned, with flat direction, the chaotic inflation, which has possible Hubble constant up to the Planck density.
The one in the shift symmetry.
Yeah. And in fact, today there was another model without shift symmetry in supergravity, which also realized chaotic inflation.
Anyway, perhaps we just want to consider this as an agenda. And first, sorry, I reported first. Look at it.
Of course.
So maybe we should conclude and thank you.